Hello, everyone, and welcome to my thesis presentation titled A Numerical Investigation of Titanic's Calm Water Maneuvering Characteristics. Before I begin, I would first like to acknowledge my principal advisor, Professor Ones, for his guidance in this investigation. I would also like to thank my reader, Professor Golden, and my editor, Professor Lutz, for their contributions to the written portion of this thesis. I would also like to acknowledge the Marine Forensics Committee by the Society of Naval Architects and Marine Engineers for providing me with the resources necessary to complete this investigation. Finally, I would like to acknowledge Charles DeRocco, author of A Quiet Sea, for inspiring me with this thesis topic. First, I will begin with a brief outline of today's presentation topics. I will start with an introduction and background, followed by a literature review. I will then state my objectives, theory, testing procedure and validation, numerical results, conclusions, and finally, I will conclude with recommendations for future work. The RMS Titanic was constructed by the Harland & Wolff shipyard in Belfast, Ireland, and was the second Olympic-class ship ordered for the White Star Line fleet. Despite the vessel's unprecedented size, Titanic passed its day-long sea trials conducted on the 2nd of April, 1912, including the demonstration of sufficient maneuvering. On the evening of the 14th of April, 1912, the ship collided with a North Atlantic iceberg while on its maiden voyage to New York. The imposed damage caused the vessel to sink in less than 3 hours, resulting in the loss of over 1,500 passengers and crew. The sinking of the Titanic led to many ramifications for the maritime industry. These included the development of the Safety of Life at Sea Convention, advancing ice patrols, and the Radio Act of 1912. Many forensic investigations were employed to better understand the chain of events that contributed to the vessel's loss. In May of 1912, both the United States and Great Britain conducted investigations in which surviving crew and passenger testimonies were recorded. Using these accounts, the British and American inquiries qualitatively concluded that the ship's failure to avoid the iceberg was due to inadequate immersive area on the ship's plate-type rudder. To gain a greater understanding of the vessel's ability to avoid obstructions, the RMS Olympic engaged in a brief controllability test in mid-1912, as described in the final Lord Mersey report developed by the British Wreck Commission. Although much of this experiment has been lost to history, a few details have been preserved. The Olympic was found to travel 466 yards in 37 seconds prior to completing a 22.5-degree change in heading. These values remain nominal. As noted later, the available plotting technology used in 1912 could only provide crude estimates of a vessel's relative location in the water with respect to time. Titanic Triumph and Tragedy by John Eaton and Charles Haas take note of the Titanic's performance during her sea trials on the 2nd of April. The ship was measured to have an advanced distance of 2,100 feet and a tactical diameter of 3,850 feet. Many historical discussions that involve the Titanic take note of her steering capability. Often, these commentaries spawn debate on whether her maneuverability was sufficient for a vessel of her size, given any operating condition and speed, citing her collision with the iceberg as evidence of insufficient rudder area and shape. Titanic Ships, Titanic Disasters by Gartsky and Woodward in 2002 take note of these arguments by comparing the ship's rudder-to-hull ratio with other passenger liners of the early 20th century. Given the D&V requirements for minimum rudder area, the Titanic employed a rudder of sufficient size to meet modern-day standards. Now that we have established the Titanic's historical context, we may now discuss the objectives of this thesis. The first objective is to improve societal understanding of Titanic's maneuverability by providing additional information to the wreck's forensic database. The second objective is to determine the calm water maneuvering characteristics of Titanic from the vessel's hydrodynamic derivatives using analytical, semi-empirical, and numerical methods. And the third objective is to determine whether the steering quality for the ship is sufficient by modern and historical standards. In continuing with the presentation, it is imperative to discuss the theory behind controllability. Ship controllability incorporates all aspects of regulating a ship's trajectory, speed, and orientation while at sea. Because of this, it is imperative to consider their impact when assessing if a design is reasonably fit for navigating through its environment. Firstly, course keeping or steering primarily focuses on the maintenance of a vessel's heading, defining the ease in which a ship can hold a course. The second sector is course changing, which investigates a vessel's ability to maneuver around objects and across various environments. As defined in Principles of Naval Architecture, Volume 3, maneuvering is the controlled change of a ship's direction of motion. Lastly, speed changing refers to the controlled change in speed, including stopping and starting. This category aims to measure the ease, rapidity, and distance covered in accomplishing changes in acceleration. This investigation focuses primarily on the first and second sectors of controllability. These components can be quantitatively expressed through a decomposition of the equations of motion. In solving traditional statics and dynamics problems, we calculate a sum of forces and moments that allow us to solve for an unknown variable. Of course, in statics, the sum of forces equals 0, while in dynamics, they result in a mass multiplied by an acceleration. The same relationship is true for ship dynamics as well, albeit with different variables and terminology. The equations of motion may be developed using two different sets of coordinate systems. An inertial frame of reference in which the coordinate system axes are fixed to the Earth, and a non-inertial frame where axes are fixed relative to the ship. In real-world testing, it is often easier to assess a vessel's maneuverability using the latter. The origin point is assumed to be the vessel's longitudinal center of gravity. The forces that materialize from hull drag, as well as the acceleration-dependent forces accumulated from the mass of the ship and the added mass of the fluid, combine to produce a total forces in surge, sway, and yaw. Ship controllability is analyzed first by considering a disturbance to a vessel operating in equilibrium. The equations of motion. This effect can be approximated using the Taylor series to linearize the equations of motion. The partial derivatives accumulated within this approximation are known as the hydrodynamic derivatives, and they are denoted as NR, NV, YR, and YV. As a first approximation in linear theory, surge forces are neglected as it is not a coupled term with the sway and yaw force, Here, we see that the sum of forces and moments equals 0, and the vessel's state of motion is in a state of equilibrium, paralleling the statics example discussed previously. We can use the hydrodynamic derivatives in sway and yaw to determine if the vessel possesses control's fixed stability. This means that in the presence of no external forces or rudder deflections, the ship will travel along a straight line course. Actuating a vessel's control surfaces, such as deflecting a ship's rudder, require an additional set of hydrodynamic derivatives that express only the hydrodynamic contributions enacted by the appendage. Accounting for these values in the vessel's equation of motion results in a non-zero sum of forces and moments. This leads us to our turning circles, which can be divided into two elementary portions. First, substantial yaw and sway accelerations temporarily occur when the vessel initially engages in a turn. Following this, the vessel experiences a steady turn in which the forward motion is constant. The three phases of the turning circle consist of the approach, the advance, and the steady turn. During the approach phase, the rudder is initially deflected while the ship maintains a constant heading. Here, the induced acceleration exists momentarily in an isolated capacity. The advance phase plays witness to the coexistence of an induced acceleration and turning velocity. In this stage, the vessel's apparent turn is initiated. During the steady turning radius phase, the accelerations are mitigated and the ship operates at a constant turning velocity. We can obtain the steady turning radius and diameter using the hydrodynamic derivatives obtained using linear and nonlinear approximation methods. Note that linear methodology only works if the vessel possesses control's fixed stability and the C value described before is greater than 0. We can also obtain the tactical diameter. Current IMO regulations and criteria state that the tactical diameter must be less than 5 ship lengths for commercial ships. Additionally, we can obtain the advanced distance, which must be less than 4.5 ship lengths in order to meet IMO criteria. Finally, the transfer distance allows us to determine the vessel's lateral translation as it turns 90 degrees from the point of initial rudder deflection. Given the relationship between hydrodynamic derivatives and a vessel's steady turning radius, it is possible to assess a vessel's calm water maneuverability via captive model testing. To develop the scope, a series of assumptions have been determined. The ship was assumed to be bare-hulled with a plate-type rudder. During the British Wreck Commissioner's inquiry of 1912, Lookout Frederick Fleet described conditions on the night of the 14th to be very calm. Using these testimonies, the analysis was completed assuming calm water conditions. Because the Titanic was a surface vessel operating in calm water, vertical motions were assumed negligible. And as was the case on the night of Titanic's collision, this assessment was completed using a service speed of 22.5 knots. And finally, the investigation assumed the vessel was operating at its design waterline. The numerical testing used for this analysis comprised of a fully viscous Reynolds average Navier-Stokes CFD solver, including a K-epsilon turbulence model for the boundary layer. Because there are very few primary sources available for indicating the ship's performance, this method of analysis was first validated using a Series 60 4211W hull with a block coefficient of 0.65. Using the Semerix Marine software compatible with Orca 3D, this hull model was tested for resistance at a variety of different operating speeds. The results were then compared with the empirical data obtained by Todd in 1963 and shown to be reasonably accurate with the published data. After validating the hull's resistance, a Series 60 model was tested under planar motion. Straight line tests were used to evaluate the model in pure sway, given drift angles from 0 to 20 degrees. Sway forces and yaw moments were recorded for each drift angle. The hydrodynamic derivatives in sway were then obtained linearly by regressing the sway forces and yaw moments of the straight line test using Taylor series. Rotating arm tests were used to evaluate the model in pure yaw, given yaw rates from 0 degrees per second to 1.2 degrees per second. Sway forces and yaw moments were recorded for each yaw rate. The hydrodynamic derivatives in yaw were then obtained using the same method as was the case in the pure sway test. The derivatives determined throughout this testing procedure were then compared with the interpolated results of the block coefficient Series 60 data published in Principles of Naval Architecture, Volume 3. The results of this test were found to also be reasonably accurate. Following validation of the numerical testing procedure, the existing hull geometry file also underwent a validation process. Using the available resources provided by the SNAME Marine Forensics Committee. First, the Rhino 7 geometry file, courtesy of the committee, was inspected for applicability in CFD modeling. Certain discrepancies were noted within this geometry file relating to its compatibility with the Semerix MP software. Additionally, the bow shape was found to diverge significantly from the geometry that is expected for this vessel. This could create significant error in predicting the vessel's directional stability. To appropriately assess these differences, an additional geometry file was created using the lines plan from the SNAME Marine Forensics Committee. To develop this model, the lines plan was first measured for scale accuracy. Although rescan distortion was present within the plan, water lines, station lines, and buttocks, as well as the particulars, were found to provide reasonably accurate measurements. The lines plan was also found to align with the general particulars indicated on several other technical drawings. These curves were then used to develop the model presented in the image to the right. To further validate the hull geometry, buttock sections were taken from each model and compared with the curvature established in the lines plan. The red sections originate from the lines itself, and the green lines represent sections taken from the new developed model. We can see a close fit in curvature between these two sources. We can also compare the station sections from the original lines plan with the redeveloped geometry. This comparison, combined with the evaluation of the model's general particulars, allow us to validate the hull shape. The model developed from the lines plan, as well as the model provided by MFC, were then tested for compliance with the stated particulars. As seen, the following design values were gathered using the measurements presented within the lines plan, as well as various technical references. Throughout the validation process, the principal particulars of the MFC model were shown to diverge from the design value. These variations were found to be mitigated within the hull model developed from the lines plan directly. Given these comparisons, we can confidently validate the redeveloped hull. Following validation of the investigation's analytical procedure and Titanic's geometry file, the ship's hull was tested using captive model, straight line, and rotating arm tests, each of which were conducted at an operating surface speed of 22.5 knots and at a design draft of about 34 feet. In cohesion with these tests, domain, time step, and mesh-dependent convergence studies pertaining to both the pure sway and pure yaw simulations were conducted in accordance with ITTC requirements. Convergence was determined through observing a decrease in error values, thereby showing a decrease in sensitivity between the obtained results and the simulation parameter. Plots of the sway force and yaw moments with respect to linear velocity are shown in the images above. Similarly to the Series 60 testing procedure, the pure sway test was completed using drift angles from 0 to 20 degrees. By regressing the results of the pure sway test, the non-dimensional pure sway velocity derivatives were found to be approximately negative 0.111, and the pure sway velocity and the yaw moment given the sway velocity was determined to be about 0.0437. Plots of the sway force and yaw moments with respect to radial velocity are shown in the images. The pure yaw tests were completed using yaw rates from 0 to 1 degrees per second. Linearizing these results yield a pure sway velocity or pure yaw velocity derivative of about 6 times 10 to the negative fifth. And the yaw moment due to sway velocity was determined to be about 7 times 10 to the negative fifth. These results align with the established theory, as the pure velocity derivatives are always negative, and the cross-coupled terms can either be negative or positive. In Titanic's case, we see that the stern dominates the yaw moment in pure sway, and the bow dominates the sway force in pure yaw. Combining these hydrodynamic derivatives yielded a positive stability index of about 0.0003. Because the C value is above 0, we can conclude that the Titanic possessed positive controls fixed stability. The hydrodynamic derivatives of Titanic's rudder were determined using the submerged rudder area found by Gartsky and Woodward in 2002, as well as the plate type rudder data published in Principles of Naval Architecture, Volume 3. Using the dimensions indicated on the lines plan, the thickness to chord ratio for Titanic's rudder was found to be approximately 0.05. Thus, data for this series was used. It is important to note that these rudder profiles were rectangular in shape, while Titanic's rudder resembled more of a semicircle, traditional for sailing vessels and older steamships of the time. These differences were assumed negligible, as a rudder's submerged area and cross-section are far more indicative of a vessel's turning capabilities than just the profile shape itself. We now have all the information we need to determine the Titanic's steady turning diameter. Although linear theory is applicable for vessels possessing controls fixed stability, this method of approximation is still limited in its ability to accurately predict a vessel's turning circle characteristics. Because of this, the Titanic's turning circle was developed by applying the hydrodynamic derivatives to a nonlinear approximation method. To do this, the obtained derivatives, as well as the vessel's general particulars, were applied to the Marine Systems Simulator MSS software MATLAB application. The developed turning circle can be visualized in the image to the right. We can see that the vessel obtained a steady turning diameter of approximately 2,664 feet, as well as a tactical diameter of about 3,773 feet. The ship also possessed an advance distance of 3,399 feet and a transfer distance of approximately 2,120 feet. As seen here, the tactical diameter to length ratio is less than 5 ship lengths, and the advance distance to length ratio is less than 4.5 ship lengths. Based off these results, the Titanic passes IMO criteria for a safe turning circle. Within this criteria, Titanic meets the requirements put forth by the IMO, and additionally, despite the qualitative conclusions put forth by the 1912 American and British wreck inquiries, Titanic possessed sufficient amount of submerged rudder area to complete an adequate turn. Although a tragic series of events caused the ship to collide with an iceberg on the 14th of April in 1912, Titanic's steady turning characteristics comply with the requirements applied to modern-day passenger vessels. From these results and comparisons, one can provide a generalized conclusion to Titanic's maneuverability and how it fits contextually with the performance observed from similarly sized ships of the early 20th century, as well as ships of the modern day. The work completed thus far has shed interesting light onto the expected trends of vessel maneuverability across time, as well as the development of larger ships with better navigational technology have led to an increase in acceptable turning radii. This makes historical sense as ship operators in the 19th and 20th centuries relied on a vessel's ability to respond to obstructions seen within eyesight. The absence of radar meant greater expectations in a ship's performance. This is especially true when considering the unusual size of the Olympic class for their time. Their novel sizes likely felt less maneuverable than what seafarers of this time were used to, whereas a modern seafarer experienced with operating ships of greater than 1,000 feet may hold different opinions. Following the completion of this investigation, I have several recommendations for future work. The first one is to assess Titanic's calm water behavior in zigzag maneuvers. This is another test that is significant in assessing a vessel's ability to avoid obstructions. The second recommendation is to assess the impact of Titanic's triple screw propulsor arrangement on course stability and maneuvering. Third is to assess the impact of waves on Titanic's turning ability. One can also validate Titanic's calm water turning characteristics using physical model tests. Lastly, one could assess the calm water turning characteristics of the RMS Oceanic from 1899, as this ship is more conventional for the time period and is often cited as being one of the most successful designs ordered by the White Star Line. Thank you very much for listening to my presentation titled A Numerical Investigation of Titanic's Calm Water Maneuvering Characteristics. I now invite the other presenters up to the podium so that we may answer any questions you might have. Thank you.